Hi everyone, this is Kalyan Kumar here, and welcome once again to Chemistry Universe. This is the last part of the Alkyl Halide series, and this is part 14, and we have titled this Polyhalides. So we're going to talk about some dihalides, we're going to talk about some trihalides, some tetrahalides, and we are going to curtail the syllabus to what is expected in the entrance exams or the competitive exams for which this is part of a syllabus. So it's going to be a short video and you will be able to see it in one go. But I always encourage you to make notes while watching the video. And whenever I give you a question, pause the video, write it down, write the question, find the answer yourself, and then check. Make the video not as a movie, but as something that you can actually watch and learn. And the only way you can do that is by making notes simultaneously. We are not in the habit of making notes while watching educational videos, but we must. Just assume that you're in a classroom and there is somebody talking to you. The only difference is there is no interaction, which is why you have to make notes, and which is why I always encourage you to ask your questions, your doubts in the comment section below. So let's begin the last part of alkyl halide. This is part 14, and this is titled Polyhalides. So here we go. And first of all, we're going to talk about dihalides. And in dihalides, there are two types of dihalides. One is called gem or geminal dihalides. Now, this is when the halogens, two halogen atoms are attached to the same carbon atom. For example, RCHCl2. Then we have Wick dihalides or vicinal dihalides. And these are the ones in which the two halogen atoms are attached to adjacent carbon atoms. Remember, there is no particular name for dihalides which are not in the same carbon or in the adjacent carbon. We simply call them as dihalides. So first, let's look at how do you prepare a geminal dihalide. Now, what happens is, we've discussed this when we did the preparation of alkyl halides. This is the reaction of PCl5 on carbonyl compounds. Now, if you remember, I told you in that reaction that whenever you have PCl5 and this has an oxygen, you'll always find that the PCl5 will take this oxygen and it will give two Cls to this, because there are two bonds which are being broken, and therefore you'll find that you get a geminal dihalide, and this is called ethylidene chloride, and of course it will give you a POCl3 as a byproduct. The same is true for ketones. You can use PBr5. The double bond O goes, you get two Brs there, and you get POBr3 coming out. The second way is by addition of halogen acids to alkynes. Now remember, alkynes, which when reacted with HBr, now one of the carbon is going to take the H plus and the other is going to take the Br minus. You get this. You get a vinyl bromide here. Now here right now I'm not writing all the kind of catalyst that you need, because it does need some catalyst. We're not going to go into the details of this reaction right now. We'll do that when we do alkynes. Now the important part is, let's assume this gets the plus, okay? And which is why the Br minus is attacking this one. And you get this. Now what happens is, if you add one more mole of HBr, now there are two options. One is the CH2, CHBr. Now the minus can go to this carbon and this can take the proton, and you get CH2 positive, and this becomes CH2Br. The other option is, this goes here, this takes the proton, meaning this becomes CH3, and this becomes CH plus Br. Now, if I were to ask you, which carbocation do you think is relatively more stable? Just look at all the effects. You will notice that it is this carbocation which is stable, because it has got 3 hyperconjugation, as well as some plus M effect of the bromine. Okay, some plus effect of the bromine, which would decrease the positive charge, despite the fact that halides have more inductive than plus M, but at least some plus M would decrease the minus side that they are having. Whereas here, it has got only two hyperconjugations and only the minus I of bromine. So this carbocation is always better. Now, if this carbocation is going to form, the Br will again attach here, and that would give you a geminal diol. Oh, sorry, a geminal dihalide. So this is what you get. So again, an alkyne, and you can add HBr to this. Obviously, here the middle carbon is the one which is going to become the plus because of hyperconjugation. And then again, this carbocation is again going to be more stable. This will take the proton and you will get CH3, you'll get more hyperconjugation, you got some plus M of Br, and that would make again a geminal dibromide. So now let's look at the preparation of vicinal dihalides. The first is addition of halogens to alkenes. This we've already done. We have an alkene, we add halogen. We did this in halogenation. We use a non-polar solvent and the two bromines get added. You get a vicinal one. Similarly, you take another alkene here and you get something similar. Then we do by the action of PCl5 on glycols. Now, glycols, if you remember, are the compounds in which the OH are on adjacent carbons. Vicinal diol. It's called ethylene glycol. And reacted with PCl5, again, remember, it takes the two O's and the two H of the O's will also get Cl. These two will get Cl. This carbon will get Cl. You will get vicinal dihalide. You will get POCl3 as well as HCl. So now let's look at some physical properties of mono and polyhalides. Now here I'm going to do the physical properties of monohalides as well, besides doing polyhalides, because they are quite interrelated and you'll get several questions regarding these in the exam. You'll be asked to compare the density or the the boiling point of polyhalides versus monohalides. You'll be asked which is lighter than water, which is heavier than water. So to be able to answer all of these physical properties are important. So I'm going to do monohalides and polyhalides, the physical properties together. All right. So here we go, physical state. Now the lower members, especially fluorine, chlorine, bromine, and even the two carbon ones of chlorine and fluorine are gases at room temperature. Rest all of them, including monoiodide and up to C18 are liquids, after which they are solids. Let's look at boiling point. Now obviously they have higher boiling point than alkanes, makes sense because they have a slightly more polarity. And the decreasing order of boiling point is Ri, Rbr, Rcl and Rf. That is simply because the greater the molecular mass, greater the size, more will be the LDF, the London dispersion forces. And that would increase the van der Waals forces overall and that would make the boiling point high. Among isomeric, we know that more branching, you will get less boiling point. So primary, secondary, tertiary. And among different polyhalogen compounds, more is the molecular mass, more would be the boiling point, which is why CCl4 has the highest boiling point compared to this, despite the fact that its dipole moment is 0 and the dipole moment of this is very high. One might feel that the dipole-dipole interactions are high, but remember the dipole moment of this is going to be very small. They're not going to be very high. And whereas here, despite the dipole moment not being any particular value, it's 0 in fact, but the induced dipole moments, those LDF values are going to be higher for CCl4. So more molecular mass does mean more boiling point. Then we have density. Now RF and RCl are lighter than water, whereas RBr and RI are heavier than water. These are facts. And decreasing order of densities again, Ri, RBr, RCl, RF. This is something you have to learn. And the densities also are dependent on the molecular mass. Then we have solubility. Now the alkyl halides are in general insoluble in water, but soluble in organic solvents. We even talk about flame test. Now, alkyl halides burn with a green flame due to their interaction with copper in the copper wire, and this is called the Bilstein test. Then you have stability. Now, when I say stability, I'm talking about stability of carbon halogen bond, and this would be, of course, RF, RCl, RBr, Ri because of the bond length. And Ri is so unstable that it ends up decomposing, giving iodine gas. So basically, iodine vapors are produced, which darken the bottle in which they are produced. And bond length, we've already discussed. F to I bond length will increase. And then the vapor phase dipole moment. Now, in the vapor phase dipole moment, there is one anomaly. The chlorides have a higher dipole moment than the fluorides and the bromides and the iodides. So the chloride is better than fluoride only because of bond length, because bond length dominates. See, there are two things that dominate between the CX bond dipole moment. One is polarity and the other is bond length, because dipole moment is a product of charge and bond length. So here bond length wins over the fact that this has greater charge. Whereas for others, the bond polarity wins over. Actually, this is more of a conclusion than something that we have predicted. Now let's look at the physical properties of dihalides specifically. The lower members are colorless, oily liquids with sweet smell, while the higher members are solids. They are all heavier than water. All the dihalides are heavier than water. Now let's look at the chemical reactions. The first reaction is that of alcoholic KOH followed by NaNH2. We'll be doing this reaction in the case of alkynes in detail, but for now you just have to assume that if you take a dihalide, either vicinal or geminal, if you react them with alcoholic KOH, there is one dehydrohalogenation. The H of this and the Cl of this go away. One H and one Cl. And you'll get this. To remove this H further and this Cl further, alcoholic KOH cannot do the job. You need a stronger base like NaNH2. Now, why do we need that? All of that detail will come in alkynes. For now, we'll just look at what the reactions are. Then you have reaction with aqueous KOH. And this is pretty simple. This we all know, that you have aqueous KOH, you'll get a glycol. And if you were to have a geminal one, you'll get an aldehyde, because one carbon having two OH won't be stable. Then we have reaction with KCN. So you have KCN reacting with vicinal, and you'll get both of CNs. And you heat this with H3 plus, you'll get acid, which if you further heat will give you an anhydride. And we'll talk again more of this when we do ketones. In ketones, we'll talk about when you'll get an anhydride, when you'll get a ketone, etc. So if you have, let's say, this is succinic acid, and this, of course, the anhydride is succinic anhydride. Suppose you have a geminal one. So geminal one will have two CNs attached to the same carbon. You do the hydrolysis of cyanides, you always get acids, remember? And here, instead of getting an anhydride, you will get decarboxylation. One COH will go and form a CO2, and you will get this. Now here I'd like to make a little bit of emphasis to make you understand. You see, what happens is, if you have CH2 n times, and you have COH at one end and COH on the other end. Now you can get the following. You can either get a cyclic ketone. You'll get a cyclic ketone, meaning one COH will go as CO2 and one of them will remain as the ketone group. You can get a cyclic anhydride, which is what you got previously. You can get a carboxylic acid. And you can even get an alkane. Now just try and understand what I'm saying. If you get a ketone, one of the COs remains, the other COH goes away as CO2. If you get an anhydride, you will just lose water from these two and you will get the anhydride. If you get an acid, again one COH goes out and you have NCH2s left. Now this H will again go with the terminal carbon of this. So that will become CH3. Since there were NCH2s and one of them have written as CH3, the remaining ones are N minus 1. And then you have one of the COH left. Then for a special case, you will get both COH going, which means you have N times CH2 and both the COH will give their H to the terminal carbons. Those two will become CH3 and the number of CH2s left now would be simply N minus 2. Now when do you get a cyclic ketone? Only when the ring is stable. Now this carbon already is a part of the ring, right? So if you want to get a 5-membered ring, 5 and 6 are stable. If you want to get a 5-membered ring, don't you think N must be 4? And if you want to get a 6-membered ring, don't you think N needs to be 5? Meaning whenever N is 4 or 5, you'll get a cyclic ketone. Now when will you get an anhydride? Remember these three are already part of the ring. So to get a 5-membered ring, don't you think N needs to be 2? And to get a 6-membered ring, don't you think N needs to be 6? Oh, sorry, 3. So when N is 2 or 3, you will get anhydride. So 2 or 3 anhydride, 4 or 5 ketone. Now this carboxylic acid happens when N is 1. When there is only one carbon between the two COH, one COH will go out as CO2, the other COH will remain and you get a carboxylic acid. And since this is happening when N is 1, this obviously means this is 0. So it is basically acetic acid. But if N is greater than 5, you will get alkane. You will get both the COH going away as CO2. And in this case, in the case of anhydride, you will see N is 2. So what do you get when N is 2? You get an anhydride, which is why you got this. And in this case, remember, between these two COH, there is only one carbon. So what happens when you have only one carbon here? One COH will go, one COH will remain, and you will get acid. Alright, so now let's talk about the next one, that is dehalogenation. And in dehalogenation, you have the vicinal one. Now you can dehalogenate, you can remove both the Cls and form a double bond, either with zinc dust in methanol or using NaI in acetone. Now how I get NaI in acetone? Because we already done Finkelstein reaction. How NaI in acetone gives me this, that we'll see later on in alkenes. But the fact of the matter is, it forms an alkene. Now let's look at the next one, trihalides. Now trihalides are CHCl3, which is chloroform. It's a colorless liquid. You have bromoform, which is also a colorless liquid. Then you have iodoform, which is a yellow colored solid, crystalline solid. We are interested in chloroform basically. The preparation of chloroform, we can start with what is known as chloral hydrate. Now this fellow is chloral hydrate. You may wonder, how is this chloral hydrate? Well, how is it stable? One carbon having two OH. Remember, these H will form hydrogen bonding with this Cl. Though technically H and Cl should not be called hydrogen bonding, it should be called dipole-dipole interaction. But yeah, we can sort of call it hydrogen bond type. But then if you heat it, of course, it becomes an aldehyde. So this is chloral hydrate. If you distill it with NaOH, you will get chloroform, you will get formate salt of sodium and water. And this is the mechanism. You have this. What do you think will happen on heating? As I said, water will be lost and you will get an aldehyde. Now OH minus is going to act as a nucleophile on the electrophilic carbon. Pi bond is going to go up. Then the pi bond is going to come down and this will grow. This will go, and that is because this is a pretty good leaving group. The negative is stabilized by the back bonding with the d orbitals of Cl as well as the minus I of Cl. And of course, this part becomes formic acid. Now, this being a stronger acid will donate a proton to this one. You will get chloroform and formate ion. And then you have a reaction with hydrogen atom in CCl4, nascent hydrogen. And in the case of iron and steam, you will get chloroform and HCl. Here you just have to learn the reaction. Now let's look at the physical properties of chloroform. Now chloroform again is a colorless, sweet smelling liquid. and it is insoluble with water but soluble in organic solvents. Excess vapors are extremely poisonous. So make sure there is no excess vapors there. It causes temporary unconsciousness. You must have seen people, trying to make people get unconscious by taking a tissue or something dosed with chloroform. But remember, that can be poisonous as well. So it is used as an anesthetic in a small amount. The boiling point of chloroform is 61 degrees Celsius. And iodoform, being a yellow crystalline solid, has a melting point of 119. You don't have to remember these values. Chloroform is best solvent for fats, oils, and wax. And if you want to look at the chemical properties of chloroform, well, one of them is oxidation with oxygen, which is a very, very difficult thing to do. I won't say difficult, but it's not a safe thing to do, because what it does is produces a poisonous gas called phosgene. So you have to be very careful about it. For this particular reason, chloroform is always kept in dark bottles away from sunlight, and made sure that it is filled up to the brim so that there is no oxygen as well. Now, if you ever want to test whether a sample of chloroform is pure or it has got phosgene, because this is done in hospitals, we first use AgNO3 solution to the chloroform, and if you get a white PPT of AgCl, it implies that this HCl is present, which will be present only when this is formed. So that indicates phosgene present. Now, if you want to remove the phosgene, well, you use 1% solution of ethanol, which will convert that into a diethyl carbonate. For example, this is the phosgene, this is ethanol, 2 molecules, and I take the H and Cl, and the C joins to the 2 O's, and you get diethyl carbonate, which is harmless. Then you have reaction with KOH, and I think you can pretty well understand 3 Cls will be replaced by OH minus, and you'll get formic acid, and then in the presence of KOH, it will become potassium formate. Then you have reaction with HNO3, and here you have chloroform, you have HNO3, the OH and the H form water, the C joins with NO2, and this is what you get as tear gas, trichloronitromethane or tear gas. Then you have reaction with acetone. So you have chloroform here, you have acetone here. Here this carbon is nucleophilic, this carbon is electrophilic. So what will happen? The nucleophilic carbon will attack the electrophilic carbon, and the H will go to O. And this is called as chlorotone, which is a hypnotic agent. Basically puts you to mild sleep. Then comes a reaction with silver powder, very important reaction for the preparation of alkynes. Just take chloroform or any trihalide, and you have Ag, then you have another trihalide. You don't have to really worry about the mechanism. Basically what happens is, of course, it looks as if the carbon is also being taken. The carbon is not taking, only the 3 halogens of the 2 carbons are taken with 6 Ag to form 6 AgCl and alkyne. Then reaction with primary amines. You have primary amine, chloroform and 3 KOH. Now this is a test for primary amines. This is called the isocyanide test, and you get an alkyl isocyanide, which has an extremely offensive smell. And this is also called the carbamine reaction, which is a test for primary amines. And then of course reaction with phenol, we call this as the Riemer-Tiemann reaction. This again we'll study in detail in phenol. I'll just give you the reaction here. You'll get salicylaldehyde, the ortho substituted one. Now let's look at the uses of chloroform. We have done pretty much everything. Chloroform is an anesthetic, while iodoform is actually an antiseptic because it gives iodine. The chloroform is a solvent for fat, waxes and rubber. And in preparation of chlorotone, a hypnotic agent, and nitrochloroform, an insecticide as well as a tear gas. Used as a preservative for anatomical specimens and as a lab reagent for identifying primary amines, we've already discussed. So now let's look at tetrahalides, the last part. Preparation, pretty simple, from methane. Now remember, the worst possible method, and I've repeated this before, the worst possible method for preparing monochloroalkanes or dichloroalkanes or trichloroalkanes is halogenation of alkanes. The best is make a tetrachloroalkane if it is methane. So you just halogenate all the hydrogens by using excess of chlorine. That will work. All right. So you have methane, chlorine, methyl chloride, then again another chlorine, the third one, the fourth one. And then let's talk about the physical properties. So now let's talk about the physical properties. The the tetrahalide is a colorless liquid with ether-like sweet smell, insoluble in water, and these are pretty simple. But it is the only organic compound which is non-combustible, so it is used in fire extinguishers, which is why we call it fire extinguisher pyrene. And some of the chemical properties are similar to chloroform. The first is oxidation. Again, it gives you phosgene gas. Then you have hydrolysis, and you know that CCl4 gets hydrolyzed. All the Cls become 4OH. You'll get CO2. CO2 in the presence of KOH will give you potassium carbonate. Then again, you have a Raymer-Tamer reaction of phenol with CCl4. The original one that we studied was chloroform. This will give you salicylic acid. Then uses of CaCl4, well, fire extinguisher pyrene, the non-polar solvent for fats, oils, and other organic compounds, the lab reagent, it's a dry cleaning agent. And lastly, we talk about freons, which are CFCs, chlorofluorocarbons. These are chlorofluoro compounds of methane, CCl2F2, and they're generally used in aerosol propellants, refrigeration, and air conditioning. But these days, we don't use them because they are the principal cause of ozone holes. And that brings us to the end of polyhalides. As I discussed earlier, I told you this is going to be a very short one. It's more of learning, less of mechanisms. And of course, there are a lot of reactions in this which we'll study separately in mechanisms in various other lessons. So ultimately, with that, we have been able to conclude alkyl halides. I hope this video was useful to you. Watch it as many times as you want. Have any questions, have any doubts, put them in the comment section below. And with that, I end this lesson, and then we'll start the next lesson, which will be aryl halides. Till then, goodbye, and thank you for watching this.